Welcome to qnawire.
This is Chapter 22, Problem 12 from the Sears and Zemansky's University Physics textbook. The nuclei of large atoms, such as uranium, with 92 protons can be modeled as spherically symmetric spheres of charge. The radius of the uranium nucleus is approximately 7.4 times 10 to the negative 15 meters. Part A, what is the electric field this nucleus produces just outside its surface? B, what magnitude of electric field does it produce at the distance of the electrons, which is about 1.0 times 10 to the negative 10 meters? And C, the electrons can be modeled as forming a uniform shell of negative charge. What net electric field do they produce at the location of the nucleus? All right, this question is just going to rely on the definition for the electric field due to a point particle at some distance r away. So that basic equation for that electric field is our electrostatic constant K, which is 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. Q being the total charge divided by r squared, where r is the distance away from that charge. All right, so we're just going to apply this to the uranium nucleus that we are interested in the problem. That total charge, well, it's 92 protons. So the total charge is 92 times the charge of one single proton, which is charge E, where E is our fundamental unit of charge of 1.60 times 10 to the negative 19 coulombs. So it's just that value E multiplied by 92 will give us the total charge of the nucleus. And then I've written down here the radius for parts A and part B. In part A, we're interested just outside the nucleus. So we're just outside. We're given the size of that nucleus is 7.4 times 10 to the negative 15 meters. So we're just outside of that. And then when we're at the distance of the electron, we're given what I'm calling RB. Just for part B, the radius that we're going is 1.0 times 10 to the negative 10 meters. So we just plug that in parts A and B. We just plug in our two values for the radius. E equals KQ over RA squared in part A. So we plug that in our universal constant K times Q, which is 92 times our fundamental unit of charge, 1.6 times 10 to the negative 19 coulombs. So that's our Q, all divided by the radius of 7.4 times 10 to the negative 15 meters, and that whole term is squared, giving us a final answer of 2.4 times 10 to the 21 newtons per coulomb for the electric field just outside the nucleus. Part B is the exact same thing, except now the radius is now our value RB. So KQ is still the same, so I'm not bothering to rewrite the numbers. It's exactly the same as we had in part A. And we're just bringing in our B, 1.0 times 10 to the negative 10 meters, substituting that in for our B, running that through the calculator, and we get 1.3 times 10 to the 13 newtons per coulomb for the answer for the electric field at the distance of the electron. And then part C, where we want to know what net electric field do they produce at the location of the nucleus that when we're inside. Well, if we model this as a spherical shell, a uniform shell, we know that all of the charges are on the surface. So if we're inside that surface, then the electric field must be equal to 0 inside the spherical shell. We know this from Gauss's law. The net electric flux is the electric field times the area A, which is equal to Q over epsilon naught. Well, inside the spherical shell, if all the charges are on the surface of the spherical shell, then the total enclosed charge is 0. So Q is equal to 0. Therefore, the only way that can happen then is if the electric field must also be 0. So you can go back and review the concept of the spherical shell to just know that the electric field is 0 inside that spherical shell, or we could also just mathematically see that using Gauss's law.